Hello and welcome to the Sleepy Physicist. I'm so glad you're here tonight. Whether you're settling into bed, curling up on your favourite chair, or simply seeking a moment of calm in your day, you've found the right place. This is where science meets serenity, where the mysteries of the universe unfold at a pace that soothes rather than overwhelms. But before we begin our journey, I have a question for you. One that might just shift how you see everything around you. Right now, as you sit there listening to my voice, you're travelling through space at over 2 million miles per hour. Not because you're on a spaceship or a rocket, but because you're riding on a cosmic carousel, spinning around something so massive, so incomprehensibly powerful, that it bends the very fabric of reality itself. And yet for most of human history, we never even knew it was there. Tonight we're going to explore Sagittarius A, the monster black hole lurking at the heart of our Milky Way galaxy. A cosmic giant so extreme that a single teaspoon of its material would weigh as much as Mount Everest. Where time itself slows to a crawl, and where the laws of physics dance on the edge of breaking down entirely. If you find these gentle explorations into the cosmos helpful for unwinding, or if you simply enjoy pondering the deeper mysteries of existence, I'd be grateful if you considered subscribing to the Sleepy Physicist. It helps more curious minds find their way here. And as always, I'm curious to know where in the world you're listening from. Tonight, feel free to share in the comments below, whether it's a quiet evening in Edinburgh or the early hours in Tokyo. You're very welcome here. Now, I do hope this video strikes the right balance between fascinating and soothing. Though I can't promise you won't learn something that might keep you thinking long after your head hits the pillow. If that happens, well, at least you'll have gained some cosmic perspective on your place in this vast universe. So settle in, get comfortable, and let's embark on a journey to the very centre of our galaxy, where space and time bend in ways that would make Einstein smile. Imagine trying to photograph something that by its very nature cannot be seen, something so dark. It swallows light itself, something 26,000 light years away. Yet so massive it holds our entire galaxy in its gravitational embrace. This was the challenge facing astronomers for decades as they tried to capture the first image of Sagittarius, a pronounced Sag A star, the supermassive black hole at the centre of our Milky Way. For most of human history, we looked up at the night sky and saw a river of stars stretching across the darkness. The Milky Way appeared to us as a gentle band of light, something peaceful and distant, but we never suspected that at its heart lay something that defies our everyday understanding of reality, a region where the normal rules simply don't apply. The story of discovering this cosmic monster begins not with telescopes pointed toward distant stars, but with a crackle of radio waves. In April 1933, Karl Jansky, one of the fathers of radio astronomy, was investigating radio interference that was disrupting transatlantic communications. What he found instead was something far more profound, a persistent radio signal coming from the direction of the constellation Sagittarius toward what we now know is the centre of our galaxy. But Jansky couldn't have imagined what was really producing those radio waves. He was detecting the faint whispers of matter spiralling into oblivion, the death screams of gas and dust as they crossed the point of no return around an object so dense that not even light could escape its pull. It would take decades before we understood what we were really looking at. The name Sagittarius A was coined for this mysterious radio source. And later, when astronomers realised the strongest emissions were coming from an incredibly compact region. At the very centre, they added an asterisk Sagittarius, a star. The asterisk, borrowed from atomic physics where it denotes an excited state, seemed fitting for something that was clearly exciting the matter around it in extraordinary ways. Think about this for a moment. Every star in our galaxy, every planet, every grain of cosmic dust, including the atoms in your own body, is slowly but inexorably orbiting this invisible giant. You're part of a cosmic dance that's been going on for billions of years, spinning around a gravitational anchor that weighs as much as 4 million of our suns compressed into a region smaller than our solar system. But here's what makes this even more remarkable. Until just a few years ago, no human being had ever actually seen Sagittarius. We knew it was there. We could measure its effects on nearby stars. We could detect the radio waves and X-rays produced by matter falling into it, but the black hole itself remained hidden, veiled by vast clouds of interstellar dust and by its own nature. The dust problem is particularly fascinating. Imagine trying to see a candle flame through a sandstorm. That's essentially what astronomers face when trying to observe the galactic centre from our position out in the spiral arms. 26,000 light years away, the space between us and Sagittarius. A is filled with cosmic dust particles that scatter and absorb visible light, making direct observation nearly impossible. This is why the centre of our galaxy looks dark, invisible light photographs. It's not that there's nothing there, it's that we're looking through what amounts to cosmic fog, so thick that it blocks almost all the light from reaching us. It's rather like being in London on a particularly foggy day and trying to make out Big Ben from across the city, except the fog extends for thousands of light years, and the object you're trying to see doesn't emit light at all. So, astronomers had to become cosmic detectives, using wavelengths of light that could penetrate this dusty veil. Radio waves, infrared radiation, and X-rays became their tools for peering into this hidden realm. And what they found was a region of space unlike anywhere else in our galaxy, a place where stars race around invisible tracks at speeds that would make your head spin literally. Some of these stars, which astronomers have nicknamed the S-stars for their proximity to Sagittarius, are moved so fast that they complete their orbits in just a few years. Imagine a star larger than our Sun, whipping around an invisible point at speeds exceeding 7,000 kilometers per second. That's fast enough to travel from London to New York in about 20 seconds. These aren't gentle planetary orbits. These are cosmic drag races with stakes measured in stellar lifetimes. The existence of these high-speed stellar orbits provided some of the strongest evidence that something incredibly massive and compact was lurking at the galactic centre. You see, there are only two things in the universe that can make stars behave like this. Either there's an enormous cluster of dark matter concentrated in an impossibly small space, or there's a black hole, and by the 1990s the evidence was pointing overwhelmingly toward the black hole hypothesis. But even as the evidence mounted, Sagittarius remained frustratingly invisible to direct observation. It was like knowing there's an elephant in a dark room because you can hear it breathing and feel the floor shake when it moves, but never quite being able to turn on the light and see it for yourself. May 12th, 2022 marked a watershed moment in human understanding. It was the day we finally saw the invisible, the day the monster at the heart of our galaxy revealed itself to human eyes for the first time in history. We had a photograph of Sagittarius, but calling it a simple photograph would be like calling the Mona Lisa a simple portrait. This image represented one of the most ambitious scientific endeavours ever attempted, involving 8 radio telescopes spread across 4 continents, working together as a single Earth-sized instrument called the Event Horizon Telescope. The image itself is both beautiful and haunting. A golden-orange ring of light surrounding a dark shadow. The ring is the accretion, disk matter spiralling into the black hole heated to billions of degrees and glowing with the intensity of stellar furnaces. The dark centre is the shadow of the black hole itself, a region where space-time is so warped that light cannot escape. What you're seeing in that image isn't actually the black hole, remember. Nothing can escape from inside the event horizon. Not even light. What you're seeing is the last gasp of matter before it crosses the point of no return. The final photons emitted by particles as they spiral inward toward oblivion. It's a cosmic funeral pyre marking the boundary between the known and the unknowable. The technical achievement required to capture this image is staggering. Think about trying to photograph a donut on the moon from Earth, except the donut is invisible and the moon is 26,000 light years away. And you have to account for the fact that space-time itself is bent around your target. Oh, and you have to coordinate 8 different telescopes on 4 different continents to work together with atomic clock precision. The data collected to create this single image filled literally tons of hard drives, so much information that it couldn't be transmitted over the internet. Instead, the drives had to be physically shipped from each telescope to processing centres, where supercomputers spent months correlating the signals. It's a testament to human ingenuity and our relentless curiosity about the universe we inhabit. But the image revealed something even more extraordinary than just the black hole's existence. It showed us that our theoretical understanding of these cosmic monsters was remarkably accurate. The size of the shadow, the brightness of the surrounding ring, even the slight asymmetry caused by matter moving at close to the speed of light, all match the predictions of Einstein's general relativity with stunning precision. This wasn't just a pretty picture. It was confirmation that our understanding of the most extreme physics in the universe was on the right track. It was Einstein getting a cosmic thumbs up from nature itself, more than a century after he first proposed that massive objects would warp space-time. The asymmetry in the image tells its own story. The bottom part of the ring appears brighter than the top. This isn't because the black hole is lopsided, it's because of something called relativistic beaming matter. And the accretion disk is moving at significant fractions of the speed of light, and when something moving that fast emits light toward you, the light appears brighter due to the Doppler effect. It's the same principle that makes an ambulance siren sound higher pitched when it's approaching you, but applied to light from matter moving at cosmic speeds. What's perhaps most remarkable is how quiet this monster actually is compared to other supermassive black holes. Sagittarius A is what astronomers call a relatively gentle giant. It's not actively devouring vast amounts of matter, like some of the more violent black holes we observe in other galaxies. Instead, it's more like a cosmic vacuum cleaner set to a low setting, occasionally gulping down a bit of gas or dust, but mostly just sitting there, warping space-time and keeping our galaxy organised. But don't let this apparent tranquility fool you. Recent observations using the James Webb Space Telescope have revealed that Sagittarius A is far from dormant. It's constantly flickering and flaring, producing bursts of infrared radiation as matter spirals inward. These flares can vary from brief flickers lasting mere seconds to sustained outbursts that continue for hours or even days. The Webb telescope observed Sagittarius A for 48 hours spread across a year, and what they found was surprising. The black hole was producing 5 to 6 major flares per day, along with numerous smaller bursts in between. It's like having a cosmic campfire that never quite goes out, sometimes burning low and steady, other times suddenly flaring up with renewed intensity. These observations revealed something else equally fascinating. The flares don't all happen at the same time. across different wavelengths of light. The shorter wavelengths change first, followed by the longer wavelengths, with delays of anywhere from a few seconds to nearly a minute. This time, delay provides clues about the physical processes occurring in the superheated plasma surrounding the black hole as particles spiral inward. They lose energy more quickly at shorter wavelengths than at longer ones, creating this cascade effect across the electromagnetic spectrum. It's rather like watching ripples spread across a pond, except the pond is made of space-time itself, and the ripples are waves of electromagnetic radiation carrying information about conditions near the event horizon of a 4 million solar mass black hole. But perhaps the most mind-bending recent discovery about Sagittarius A concerns its spin and orientation. Detailed analysis of the Event Horizon Telescope. Data enhanced by machine learning algorithms has revealed that our galactic center black hole is spinning at nearly its maximum possible rate, somewhere between 80 and 90% of the theoretical limit, and its axis of rotation points almost directly at Earth. This alignment is extraordinary. Imagine spinning a top and having it point straight at you from across the room. Now imagine that top weighs 4 million times as much as our Sun and is spinning so fast that space-time itself is dragged along like honey stirred with a cosmic spoon. The implications of this discovery extend far beyond mere curiosity. A rapidly spinning black hole creates what physicists call frame dragging, an effect where the rotation of the black hole literally twists space-time around it like water swirling down a drain. This twisted space-time affects everything in the vicinity, including the orbits of nearby stars and the behaviour of the accretion disk itself. And there's more. The fact that Sagittarius A is spinning so rapidly suggests something profound about its formation. History, black holes don't just appear fully formed, they grow over billions of years by accreting matter and merging with other black holes. The spin rate of Sagittarius A tells us that it likely formed from the collision of two massive black holes in the distant past. A cosmic merger that would have sent ripples through space-time itself. As we continue our exploration of this cosmic giant, we'll discover how its presence shapes not just our galaxy, but our very existence. How the dance of stars around its invisible mass has taught us about the nature of space-time itself, and how recent discoveries are forcing us to reconsider what we thought we knew about the most extreme objects in the universe. But that's a story for our next chapter, where we'll journey even deeper into the realm where physics becomes philosophy, and where the monster at the center of our galaxy reveals secrets about the very fabric of reality itself. There's something almost poetic about the way science works. We spend centuries developing theories, crafting mathematical equations, and making predictions about how the universe should behave. But then nature has to have the final word. And nowhere is this conversation between theory and reality more dramatic than in the extreme environment surrounding Sagittarius A, where the universe's most fundamental laws are pushed to their absolute limits. Einstein's general relativity, proposed in 1915, made some rather audacious claims about the nature of space and time. It suggested that what we experience as gravity isn't really a force at all, but rather the curvature of space-time itself. Massive objects, Einstein proposed, warp the fabric of reality like a bowling ball placed on a stretched rubber sheet. It was an elegant theory, mathematically beautiful, but for decades it remained largely in the realm of theoretical physics. But Sagittarius A has become nature's own laboratory for testing these ideas under the most extreme conditions imaginable. Here, space-time isn't just gently curved, it's twisted into knots, stretched to breaking point, and warped beyond anything we experience in our everyday lives. And remarkably, Einstein's century-old equations have passed every test with flying colours. Consider the star known as S2, one of the most closely watched objects in our galaxy. This stellar performer completes a full orbit around Sagittarius A every 16 years. But it's not following the kind of neat, predictable ellipse that planets trace around our Sun. Instead, S2's orbit precesses. It shifts slightly with each revolution, tracing out a pattern that looks rather like a flower with multiple petals. This precession isn't random. It's a direct consequence of the intense gravitational field near the black hole, exactly as Einstein's equations predicted. Each time S2 completes an orbit, its path shifts by about 12 arc minutes, roughly 1/5 of a degree. It might not sound like much, but detecting this tiny shift required some of the most precise astronomical measurements ever made. It's like measuring the width of a human hair from a distance of several kilometers, but S2 isn't the most extreme example we've discovered. There's an even more remarkable star, designated S4714, which holds the current record for the closest approach to our galactic centre. This stellar daredevil swoops in to within about 12 astronomical units of Sagittarius A, roughly the distance from our Sun to Saturn, travelling at nearly 8% of the speed of light during its closest approach. Let that sink in for a moment. We're talking about an object larger than our Sun, made of hundreds of billions of tons of matter, moving at 24,000 kilometers per second. That's fast enough to circle the Earth in about 2 seconds. And it's doing this while experiencing gravitational forces so intense that time itself behaves differently. This is where things become truly mind-bending. As S4724 approaches the black hole, time begins to slow down relative to our perspective here on Earth. It's not that the star's clocks are running slow. From the star's point of view, everything is perfectly normal. But from our distant vantage point, we would see the star's processes appearing to slow down as it enters the region of intensely curved spacetime. This effect, called gravitational time dilation, isn't science fiction. It's measurable reality. GPS satellites orbiting Earth have to account for a much weaker version of this same phenomenon. Their clocks run slightly faster than identical clocks on Earth's surface because they're in a weaker gravitational field. Without correcting for this effect, GPS would accumulate errors of several kilometers per day. But near Sagittarius A, these effects become dramatic. If you could somehow watch S14 from a safe distance as it made its closest approach, you'd see the star apparently slow down as it entered the black hole's most intense gravitational embrace. Any light emitted by the star would be shifted toward the red end of the spectrum, stretched by the warping of space-time itself. The recent discovery that Sagittarius A is spinning at nearly maximum velocity adds another layer of complexity to this cosmic physics experiment. A spinning black hole doesn't just warp space-time, it drags it along like a whirlpool. This effect, called frame dragging, means that anything orbiting near the black hole gets caught up in this twisted space-time and carried along with the rotation. Imagine trying to swim upstream in a river where the current itself is being twisted into spirals. That's essentially what matter experiences in the vicinity of a rapidly rotating black hole. The very coordinates of space and time become mixed up, creating a region where the normal rules of cause and effect start to blur. This frame-dragging effect has practical consequences for everything orbiting near Sagittarius A. The accretion disk, that glowing ring of matter we see in the Event Horizon Telescope image, isn't just heated by friction as particles spiral inward. It's also being twisted and distorted by the black hole's rotation, creating complex magnetic field patterns that can launch jets of material at nearly the speed of light. But here's what makes this even more fascinating. The discovery that Sagittarius A's spin axis points almost directly at Earth isn't just a cosmic coincidence. This alignment gives us a unique perspective on the physics of rotating black holes. We're essentially looking down the barrel of a 4 million solar mass cosmic engine, seeing effects that would be impossible to observe from any other angle. The polarized light patterns we observe from this perspective reveal the structure of magnetic fields in the accretion disk, showing us how matter behaves in conditions that we could never recreate in any earthly laboratory. The plasma surrounding Sagittarius A reaches temperatures of billions of degrees, hot enough that individual atoms are stripped of their electrons, creating a soup of charged particles that responds to magnetic fields in complex ways. Recent observations have revealed something even more extraordinary about this environment. The accretion disk around Sagittarius A appears to be in a state of constant turbulence, with matter not flowing smoothly inward, but instead forming complex patterns of instability. These patterns create the flares and bursts of radiation that the James Webb Space Telescope detected, sudden brightening events that can increase the black hole's luminosity by factors of 10 or more within minutes. Each flare represents a moment when the delicate balance between gravity, magnetic fields, and thermal pressure breaks down temporarily. Perhaps a clump of matter suddenly plunges inward, or magnetic field lines reconnect violently, or the accretion disk develops an instability that propagates like a wave. The exact mechanisms are still being studied, but what's clear is that the environment around Sagittarius A is far more dynamic and chaotic than we once imagined. This chaos isn't random though. It follows patterns that reveal deep truths about the nature of matter under extreme conditions. The time delays between flares at different wavelengths, for instance, tell us about how particles lose energy as they spiral toward the black hole. The polarization of the emitted light reveals the structure of magnetic fields. Even the apparent randomness of the flaring activity contains information about the fundamental physics governing accretion onto black holes. What emerges from all these observations is a picture of Sagittarius A as not just a gravitational monster, but as a complex dynamic system where gravity, electromagnetism, and the properties of matter at extreme temperatures all interact in intricate ways. It's simultaneously one of the most violent environments in the universe and one of the most precisely ordered, where chaos and pattern dance together in ways that challenge our understanding. The study of Sagittarius A has also forced us to confront some of the deepest questions in physics. What happens to information that falls into a black hole? How do quantum mechanics and general relativity reconcile in the extreme conditions near the event horizon? These aren't just abstract theoretical puzzles, they're questions that have direct bearing on our understanding of reality itself. As we've watched stars orbit this invisible giant, as we've captured its shadow in radio waves, as we've measured the precise ways it warps space-time, we've been engaged in something profound. We've been testing the very foundations of our understanding of the universe, and remarkably, those foundations have held firm. Einstein's equations, formulated over a century ago, continue to predict the behavior of matter and energy in conditions he could never have imagined. But perhaps the most remarkable thing about Sagittarius A isn't what it confirms about our theories, it's what it reveals about the universe's capacity for extremes. Here is an object so dense that a sugar cube's worth of its material would weigh as much as all of humanity. Here is a region where time flows differently, where space itself is twisted into impossible geometries, where the normal concepts of inside and outside lose their meaning. And yet this monster isn't destroying our galaxy, it's organizing it. The gravitational influence of Sagittarius A helps maintain the spiral structure of the Milky Way, keeps star formation rates regulated, and provides the central anchor around which hundreds of billions of stars, including our own Sun, perform their cosmic dance. In many ways, Sagittarius A embodies one of the most beautiful aspects of physics, the way extreme conditions don't break the laws of nature, but rather reveal them in their purest form. Like a master craftsman whose skill becomes most apparent when working with the most challenging materials, the universe displays its deepest principles most clearly in its most extreme environments. As we continue our journey deeper into the heart of darkness, we'll discover how this monster black hole shapes not just space and time, but life itself. We'll explore the surprising ways that Sagittarius A influences the very conditions that make planets, stars, and perhaps even consciousness possible. The story of our galactic center is ultimately the story of how chaos and order, destruction and creation, darkness and light are all part of the same cosmic symphony. There's a beautiful paradox at the heart of our galaxy. The very center, dominated by a gravitational monster that devours everything in its path, is also one of the most fertile regions for star formation in the entire Milky Way. It's like discovering that the most dangerous neighborhood in the city also happens to have the most vibrant community garden. This contradiction has puzzled astronomers for decades and led to some surprising discoveries about how life and death dance together on cosmic scales. When we think about star formation, we usually picture quiet, cold regions of space where vast clouds of gas and dust slowly collapse under their own gravity over millions of years. These stellar nurseries are typically far from any major gravitational disturbances, peaceful cosmic suburbs where new suns can form without interference. The last place you'd expect to find baby stars is in the immediate vicinity of a supermassive black hole, and yet that's exactly what we observe around Sagittarius A. Within just a few light years of the black hole, a distance that's practically touching in astronomical terms, we find not just ancient stars that have somehow survived the gravitational maelstrom, but young stars that couldn't be more than a few million years old. Some are so young, they're practically still in their cosmic cribs. This discovery initially baffled scientists. How could stars possibly form in such a hostile environment? The tidal forces near Sagittarius A should tear apart any gas cloud before it could collapse to form a star. The intense radiation from the black hole's accretion disk should heat any nearby gas to temperatures far too high for star formation. By all rights, the galactic center should be a stellar desert, not an oasis, but nature, as always, proved more creative than our initial assumptions. Recent observations using radio telescopes have revealed the signatures of what astronomers call protoplanetary disks, or proplids, in the region around Sagittarius A. These are the cosmic cocoons where new stars are born, surrounded by disks of gas and dust that will eventually form planetary systems. The discovery of these proplids just 2 light years from Sagittarius A suggests that star formation near supermassive black holes isn't just possible. It might actually be easier than in other parts of the galaxy. The key lies in understanding how gravity works on different scales. While the black hole's tidal forces can indeed tear apart large structures, they can also compress smaller regions of gas to densities high enough to trigger collapse. It's rather like the difference between trying to squeeze a beach ball and trying to squeeze a marble. The beach ball will deform and eventually pop under pressure, but the marble becomes denser and more solid. In the environment around Sagittarius A, small dense clumps of gas can be compressed by the black hole's gravity and the shock waves from stellar winds until they reach the critical density needed for star formation. But these aren't ordinary star-forming regions. The proplyds near Sagittarius A are being blasted with ultraviolet radiation, thousands of times more intense than anything we experience in our quiet corner of the galaxy. This radiation heats the gas in the protoplanetary disks and strips it away in streams, creating bow shocks that glow in infrared light. It's like trying to grow a garden in a cosmic hurricane while being pelted with high-energy particles. Yet somehow, stars not only form in these extreme conditions, they thrive. The intense radiation that might seem destructive actually plays a crucial role in regulating the star formation process. It prevents the protoplanetary disks from growing too massive, ensuring that the resulting stars are primarily low-mass objects rather than the massive short-lived giants that would quickly exhaust their fuel and explode. This process has created what astronomers call the paradox of youth in the galactic center. We observe clusters of young massive stars orbiting very close to Sagittarius A. Stars like the famous S stars we discussed earlier. These stellar speed demons are only a few million years old, which in cosmic terms makes them practically newborns. But they shouldn't exist at all. The puzzle is this: massive stars have short lifespans, typically burning through their fuel in just a few million years before exploding as supernova. If these stars formed where we see them now, so close to the black hole, they should have been torn apart by tidal forces long before they could complete their formation. But if they formed further away and somehow migrated inward, the journey should have taken longer than their total lifespan. Recent research suggests a fascinating solution to this paradox. It appears that star formation near Sagittarius A doesn't happen gradually and peacefully, as it does in other parts of the galaxy. Instead, it occurs in sudden, intense bursts triggered by the infall of massive gas clouds. When a giant molecular cloud, containing perhaps millions of times the mass of our Sun, falls toward the galactic center, it gets compressed and heated to extraordinary densities. Under these extreme conditions, the normal timescales of star formation are dramatically accelerated. Instead of taking millions of years to form, stars can condense from the gas in just thousands or tens of thousands of years. This rapid formation process creates entire clusters of stars, almost simultaneously, populating the region around the black hole with young massive objects before tidal forces have time to disrupt the process. The discovery of ongoing star formation so close to Sagittarius A has profound implications for our understanding of galactic evolution. It suggests that supermassive black holes aren't just cosmic vacuum cleaners, indiscriminately devouring everything in their vicinity. Instead, they're more like cosmic gardeners, simultaneously destroying and creating, maintaining a delicate balance between growth and decay. This balance is evident in what astronomers call the central molecular zone, a region extending about 1/500 light-years from the galactic center. Despite being less than 1% of the galaxy's volume, this region has produced up to 10% of all the stars formed in the Milky Way over the past 100 million years. It's an extraordinary concentration of stellar birth in what should be, by all conventional wisdom, a stellar graveyard. The gas clouds in this region behave unlike those anywhere else in the galaxy. Instead of being cold and quiescent, they're hot, turbulent, and shot through with complex filamentary structures. They're constantly being stirred and compressed by the gravitational influence of Sagittarius A, by shock waves from stellar explosions, and by the complex interplay of magnetic fields and cosmic rays. Computer simulations of this environment reveal a landscape that's both chaotic and beautiful. Gas flows in complex spirals, forming bridges and streams that connect different star-forming regions. Shock fronts propagate through the medium like cosmic tsunamis, triggering star formation in some regions while disrupting it in others. It's a three-dimensional tapestry of creation and destruction, playing out on scales so vast that light takes years to cross from one side to the other. One of the most intriguing discoveries in this region is an object known as the Brick, a massive, dense cloud of molecular gas that, despite its name, is anything but solid. The Brick is one of the most massive star-forming regions in the galaxy, containing enough material to form hundreds of thousands of stars. Yet it shows no signs of active star formation at all. The Brick appears to be a stellar nursery in waiting, a region where all the conditions for star formation are present, but something is preventing the process from beginning. It's like a pile of kindling that's perfectly dry and ready to burn, but missing the spark. Understanding why the Brick remains dormant while nearby regions burst with stellar birth is one of the key puzzles in galactic center astronomy. Recent observations suggest that the Brick's quiescence might be temporary. Computer models show that objects like the Brick are constantly being compressed and stretched by their orbital motion around the galactic center. As the Brick follows its path around Sagittarius A, it experiences varying gravitational forces that could eventually trigger a massive burst of star formation. When that happens, and astronomers believe it will within the next few million years, the Brick could produce one of the most spectacular episodes of star formation in the galaxy's recent history. Hundreds of thousands of new stars could ignite almost simultaneously, illuminating the galactic center with a brilliance that would be visible from other galaxies. This cyclical nature of star formation in the galactic center reveals another layer of the complex relationship between Sagittarius A and its surroundings. The black hole doesn't just influence individual stars and gas clouds, it orchestrates the entire rhythm of stellar birth and death in the central regions of our galaxy. It's like a cosmic conductor, using gravity as its baton to direct a symphony that plays out over millions of years. The implications of this relationship extend far beyond our own galaxy. Supermassive black holes are found at the centers of virtually all large galaxies, and the connection between these monsters and their host galaxies appears to be fundamental to how cosmic structures form and evolve. The mass of a galaxy's central black hole correlates remarkably well with the mass of the galaxy's central bulge of stars, suggesting a deep evolutionary connection. This connection implies that the story of Sagittarius A is, in many ways, the story of the Milky Way itself. As our galaxy formed and grew over billions of years, the central black hole grew alongside it, regulating star formation, processing gas and dust, and maintaining the delicate balance between order and chaos that characterizes galactic evolution. But the influence of Sagittarius A extends even further than the regulation of star formation. Recent discoveries have revealed that our galactic center is also a source of some of the highest energy particles in the universe, cosmic rays that travel at nearly the speed of light and can penetrate through entire galaxies. These particles, accelerated by the complex magnetic fields around the black hole, carry energy and information across vast distances, potentially influencing the evolution of life itself. As we prepare to delve even deeper into the mysteries of our galactic center, we'll explore how this cosmic monster shapes not just the structure of our galaxy, but the very conditions that make planets, chemistry, and perhaps even consciousness possible. The story of Sagittarius A is ultimately the story of how the most extreme objects in the universe can create the conditions for the most delicate phenomena, including the emergence of beings capable of contemplating their own cosmic origins. But what if I told you that right now, as you listen to these words, particles that were born in the heart of our galaxy are passing through your body? Not metaphorically, but literally. Cosmic rays, subatomic bullets, travelling at 99% the speed of light, streaming through you at this very moment, carrying with them the signature of Sagittarius A's violent processes. These invisible messengers have journeyed for thousands of years across the galaxy to reach you, and their story reveals perhaps the most surprising role our central black hole plays in the cosmic order. To understand how Sagittarius A became a cosmic particle accelerator, we need to venture into the realm where magnetism and gravity dance together in ways that would make a physicist's head spin. Around every black hole, the churning of matter in the accretion disk creates magnetic fields of unimaginable strength, billions of times more powerful than Earth's magnetic field. These aren't the gentle, orderly field lines you might remember from school science experiments, with iron filings and bar magnets. These are chaotic, writhing serpents of magnetic force that stretch and snap like cosmic rubber bands. When these magnetic field lines reconnect, a process that sounds deceptively gentle but releases energy equivalent to billions of nuclear bombs. They launch particles into space at velocities that approach the fundamental speed limit of the universe. It's rather like a cosmic slingshot, except instead of launching stones, it's hurling protons, electrons, and heavier atomic nuclei across galactic distances. Some of these particles become trapped in the magnetic fields surrounding Sagittarius A, spiraling around the black hole in complex orbits that gradually accelerate them to higher and higher energies. Others escape entirely, streaming outward through the galaxy as cosmic rays. These particles carry with them information about the conditions near the event horizon, becoming cosmic archaeologists that preserve evidence of processes we could never observe directly. The energy scales involved here are almost incomprehensible. The most energetic cosmic rays detected from the galactic center carry more energy in a single particle than a baseball thrown by a major league pitcher. But remember, these aren't baseballs, they're individual protons, particles so small that trillions of them could fit on the head of a pin. Concentrating that much energy into something so tiny requires processes that operate at the very limits of what physics allows. What makes this even more remarkable is that these cosmic messengers don't just tell us about Sagittarius A. They may have played a crucial role in making life possible throughout the galaxy. When cosmic rays interact with Earth's atmosphere, they trigger cascades of secondary particles that shower down to the surface. These particle showers have been bombarding our planet for billions of years, and some scientists believe they may have contributed to the mutations that drove evolution forward. It's a fascinating thought. The monster at the center of our galaxy, through its production of high-energy particles, may have inadvertently helped create the very diversity of life we see around us. Every cosmic ray that strikes Earth's atmosphere is, in a sense, a letter in a message that's been travelling across the galaxy for millennia, carrying information from the most extreme environment in our cosmic neighbourhood. But Sagittarius A doesn't just send out individual particles, it also launches massive outflows of material that shape the structure of our entire galaxy. Recent observations have revealed what astronomers call the Fermi bubbles, enormous structures of hot gas extending 25,000 light-years above and below the galactic centre. These bubbles, invisible to optical telescopes, but glowing brightly in gamma rays, are thought to be the remnants of a much more active phase in Sagittarius A's history. Picture, if you will, a cosmic soap bubble blown by a black hole. Except this bubble is larger than our entire local group of galaxies, filled with gas heated to millions of degrees, and glowing with the light of the most energetic photons in the universe. The Fermi bubbles represent one of the largest structures associated with our galaxy, and they're a testament to the incredible power that Sagittarius A can unleash when it's actively feeding. These bubbles likely formed during an episode when our normally quiet black hole suddenly encountered a large meal, perhaps a gas cloud or even another, smaller black hole. During this feeding frenzy, which may have occurred just a few million years ago, Sagittarius A would have shone with the brightness of millions of suns, launching jets of material at nearly the speed of light. These jets carved out cavities in the surrounding gas, creating the bubble structures we see today. The existence of the Fermi bubbles tells us something profound about the nature of supermassive black holes. They're not steady, predictable objects. Instead, they're capable of dramatic changes in behaviour that can affect entire galaxies. Sagittarius A has been relatively quiet during human history, but on cosmic timescales, it experiences periods of violent activity that reshape its entire environment. This variability has important implications for understanding galactic evolution. During active phases, supermassive black holes can inject enormous amounts of energy into their surroundings, heating gas to temperatures that prevent star formation and potentially driving material completely out of the galaxy. During quiet phases like the current one, gas can cool and collapse, allowing new generations of stars to form. It's this regulation of star formation that reveals perhaps the most subtle and important role that Sagittarius A plays in our galaxy's ecology. Like a cosmic thermostat, it maintains a delicate balance between too much and too little star formation. Without this regulation, galaxies either burn through all their gas too quickly, creating a brief burst of stars followed by sterility, or they remain too cold and quiescent to form stars at all. The precision of this balance is truly remarkable. Computer simulations show that if Sagittarius A were significantly more or less massive, our galaxy would look completely different. A more massive black hole would suppress star formation too strongly, creating a galaxy filled mostly with old red stars. A less massive black hole wouldn't provide enough regulation, leading to chaotic bursts of star formation that would quickly exhaust the galaxy's gas supply. Instead, we find ourselves in what appears to be a cosmic Goldilocks zone, where the mass of our central black hole is just right to maintain the kind of steady, regulated star formation that has allowed complex chemistry and ultimately life to develop over billions of years. It's yet another example of the remarkable fine-tuning that characterizes our universe, where slight changes in fundamental parameters would result in a cosmos incapable of producing the complexity we observe. Recent studies have also revealed that Sagittarius A influences the galaxy through more subtle mechanisms. The gravitational waves produced by matter spiraling into the black hole, though far too weak to detect directly, propagate throughout the galaxy at the speed of light. These ripples in spacetime carry away energy and angular momentum, affecting the long-term evolution of orbiting matter. Over billions of years, these gravitational waves have been slowly but steadily removing energy from the galactic center, causing orbiting gas and stars to spiral inward. This process, called gravitational wave-driven orbital decay, operates on timescales so long that its effects are barely perceptible even over geological time. Yet it represents another way that Sagittarius A shapes its environment, demonstrating how even the most subtle effects can accumulate over cosmic time to produce significant changes. The study of these various influence mechanisms has revealed something unexpected about the relationship between supermassive black holes and their host galaxies. Rather than being separate objects that happen to occupy the same space, they appear to be intimately connected, evolving together in a cosmic symbiosis that has persisted for billions of years. This symbiosis extends beyond our own galaxy. Observations of distant galaxies reveal that the properties of supermassive black holes correlate remarkably well with the properties of their host galaxies. More massive galaxies tend to have more massive central black holes, and the relationship is so precise that astronomers can predict the mass of a galaxy's black hole just by measuring the velocity dispersion of stars in the galaxy's central bulge. This correlation, known as the M-sigma relation, suggests that the growth of supermassive black holes and the formation of galactic structures are fundamentally linked processes. As galaxies form through the merger of smaller structures, their central black holes merge as well, growing in mass and influence. The energy released during these mergers helps regulate star formation and may even determine the final mass and structure of the resulting galaxy. Understanding this relationship has become one of the key goals of modern astrophysics because it connects the smallest scales, the event horizons of black holes, with the larger scales, the structure of the cosmic web itself. Sagittarius A, as our nearest and best studied supermassive black hole, serves as a crucial laboratory for understanding these connections. But perhaps the most profound realization to emerge from decades of studying our galactic center is this: we are not separate from Sagittarius A. We are part of its sphere of influence. Every atom in your body, every breath you take, every thought you think exists within the gravitational embrace of this cosmic monster. You are, quite literally, a citizen of a black hole's domain. This isn't cause for alarm. Sagittarius A is far too distant to pose any direct threat to Earth or our solar system, but it does provide a remarkable perspective on our place in the cosmos. We exist within a vast, complex system where the most extreme objects in the universe create the conditions necessary for the most delicate phenomena. The monster at the center of our galaxy doesn't just organize stars and gas, it helps create the stable, long-term environment that makes planets, chemistry, and consciousness possible. As we continue our journey deeper into the heart of darkness, we'll explore how recent discoveries are revealing new mysteries about Sagittarius A that challenge our understanding of black holes themselves. We'll discover binary stars dancing impossibly close to the event horizon and learn how these cosmic waltzes are rewriting the textbooks on stellar evolution in extreme environments. In December 2024, astronomers made a discovery that shouldn't have been possible. they found two stars locked in an eternal dance, orbiting each other in the immediate vicinity of Sagittarius A. These binary stars, designated D9, are performing what may be the most precarious waltz in the universe, spinning around each other while simultaneously careening around our galaxy's supermassive black hole at velocities that would make your head spin. Quite literally. To understand why this discovery is so extraordinary, imagine trying to waltz in the middle of a hurricane while riding on a carousel that's spinning at 1,000 miles per hour. The gravitational environment around Sagittarius A should be far too turbulent, far too violent to allow two stars to maintain the delicate gravitational embrace required for a stable binary orbit. And yet, there they are, defying our expectations and teaching us something new about how the universe works. The story of D9 begins with youth, cosmic youth that is. At just 2.7 million years old, these stars are practically infants by astronomical standards. Our own Sun, by comparison, has been shining for 4.6 billion years and is considered middle-aged. But youth in this case may be exactly what's allowed D9 to survive in such an extreme environment. Young binary star systems are typically more tightly bound than their older counterparts. The two stars in D9 orbit each other at a distance comparable to the space between our Sun and Uranus, close enough that their mutual gravitational attraction can withstand the disruptive tidal forces from Sagittarius A. It's rather like two dancers holding hands tightly enough to maintain their partnership, even while being jostled by a crowd. But this discovery raises profound questions about stellar formation in extreme environments. How did these two stars manage to form so close together in the chaotic gravitational field near our galactic center? The traditional model of binary star formation involves the fragmentation of a collapsing gas cloud into two separate condensations that then contract to form stars. But near Sagittarius A, the intense tidal forces should prevent such fragmentation from occurring. One possibility is that D9 formed further from the black hole and then migrated inward, perhaps as part of a larger star cluster that was gradually disrupted by tidal forces. As the cluster dissolved, most of its stars were flung outward or consumed by the black hole, but the binary system, D9, being more tightly bound than individual stars, managed to survive the journey inward. Another intriguing possibility is that D9 represents a new mode of star formation that can only occur in the extreme environment near supermassive black holes. Recent theoretical work suggests that the intense gravitational fields and complex gas dynamics near Sagittarius A might actually facilitate the formation of binary systems under certain conditions. The same tidal forces that would tear apart a loosely bound system might compress and stabilize a more compact binary. Whatever the formation mechanism, D9's existence has already revealed something unexpected about stellar evolution in extreme environments. Computer models predict that the two stars will eventually merge within the next few million years, unable to maintain their delicate balance against the increasingly disruptive effects of their proximity to Sagittarius A. When this merger occurs, it will create a single, more massive star that may follow a completely different evolutionary path than stars formed in more quiescent regions of the galaxy. The discovery of D9 also provides a new tool for probing the gravitational environment around Sagittarius A. As the binary system orbits the black hole, the timing of eclipses between the two stars can be measured with extraordinary precision. Any deviation from the predicted eclipse times would indicate the influence of gravitational waves, frame-dragging effects, or other relativistic phenomena that are too subtle to detect through other means. It's remarkable to think that by watching two distant stars eclipse each other, we can test Einstein's equations in one of the most extreme gravitational environments in the universe. Each eclipse of D9 is essentially a cosmic experiment in general relativity, carried out on scales and in conditions that we could never replicate in any earthly laboratory. But D9 isn't the only surprise that Sagittarius A has revealed recently. Advanced analysis of data from the Event Horizon Telescope has uncovered evidence for what appears to be a hotspot in the accretion disk, a region of superheated plasma that orbits the black hole like a cosmic ember circling a celestial campfire. This hotspot completes an orbit every 70 minutes, travelling at roughly 30% the speed of light. The existence of this hotspot provides a direct window into the dynamics of matter in the final moments before it crosses the event horizon. As the hotspot orbits, it experiences the full effects of Einstein's general relativity, time dilation, frame dragging, and the warping of spacetime itself. By tracking its motion, astronomers can map the gravitational field around Sagittarius A with unprecedented precision. What they've found is both confirmation of our theoretical understanding and hints of new physics yet to be discovered. The hotspot's orbit precesses, or shifts, with each revolution, exactly as Einstein's equations predict. But there are subtle variations in its behaviour that may indicate the presence of additional effects, perhaps quantum mechanical corrections to general relativity that only become apparent in the most extreme gravitational fields. These observations are pushing our understanding of black hole physics into uncharted territory. Near the event horizon of Sagittarius A, the curvature of spacetime becomes so extreme that quantum effects, normally negligible on macroscopic scales, may begin to play a significant role. The boundary between classical and quantum physics becomes blurred, and new phenomena may emerge that we're only just beginning to glimpse. One of the most intriguing possibilities is that the event horizon itself may not be the smooth, well-defined boundary that classical general relativity predicts. Quantum effects might create a fuzzy region around the black hole where the normal concepts of space and time begin to break down. This quantum fuzziness might manifest as subtle variations in the behaviour of matter and light near the event horizon, variations that could potentially be detected through careful observation of objects like the hot spot in Sagittarius A's accretion disk. The implications of such discoveries would extend far beyond black hole physics. They would provide our first direct evidence for quantum gravity, the long-sought theory that unifies Einstein's general relativity with quantum mechanics. For nearly a century, physicists have struggled to understand how these two pillars of modern physics fit together. The extreme environment around Sagittarius A may finally provide the laboratory where this grand unification can be tested and refined. But even as we push the boundaries of fundamental physics, Sagittarius A continues to surprise us with phenomena that challenge our basic assumptions about how black holes behave. Recent observations have revealed that the accretion disk around our galactic centre doesn't always flow smoothly inward, as simple models predict. Instead, it appears to develop instabilities and turbulent eddies that can temporarily halt or even reverse the inflow of matter. These instabilities create a complex, ever-changing landscape around the black hole. Material that was spiralling inward might suddenly be ejected outward in a burst of energy. Gas that seemed destined to cross the event horizon might instead be heated to billions of degrees and launched into space as a high-energy jet. The accretion disk becomes less like a smooth whirlpool and more like a cosmic storm system, with high-pressure regions, low-pressure zones, and sudden violent weather fronts. This turbulent behavior has profound implications for our understanding of how black holes grow and evolve. If the accretion process is highly variable and unpredictable, it means that the growth of supermassive black holes may be far more episodic than we previously thought. Rather than steadily increasing in mass over billions of years, black holes like Sagittarius A may go through long periods of relative quiet punctuated by brief episodes of rapid growth. This episodic growth model helps explain some puzzling observations about supermassive black holes in the early universe. Astronomers have discovered black holes with masses of billions of suns that formed when the universe was less than 1 billion years old, not enough time for steady accretion to build such massive objects. But if black holes can undergo periods of extremely rapid growth, during which they consume matter at rates far exceeding the normal theoretical limits, these early monsters become much more plausible. The study of Sagittarius A's feeding habits is thus providing insights not just into our own galactic centre, but into the formation and evolution of supermassive black holes throughout cosmic history. Each flare, each burst of activity, each moment of apparent indigestion in our local black hole tells us something about the processes that shape the universe's largest and most influential objects. As we've journeyed deeper into the mysteries of Sagittarius A, we've discovered that this cosmic monster is far more complex, far more dynamic, and far more influential than anyone imagined when it was first detected as a radio source nearly a century ago. It's not just a gravitational anchor holding our galaxy together, it's an active participant in galactic evolution, a laboratory for testing the most fundamental laws of physics, and perhaps even a contributor to the conditions that made life possible. But our exploration is far from over. The monster at the centre of our galaxy still holds secrets that may revolutionize our understanding of space, time, and the very nature of reality itself. As new telescopes come online and new techniques are developed, we're poised to peer even deeper into the heart of darkness and discover what other surprises await us there. There's something almost musical about the way Sagittarius A orchestrates the cosmic dance around it. Every star, every particle of gas, every ripple of electromagnetic radiation follows patterns that, when translated into sound, would create a symphony of unimaginable complexity. But the most ethereal music of all comes from something we cannot see, cannot touch, cannot directly observe: the gentle vibrations in the fabric of spacetime itself. Gravitational waves, those ripples in the very foundation of reality, are constantly being generated by the complex choreography around our galactic centre. When binary stars like D9 spiral around each other, they create tiny perturbations in spacetime that propagate outward at the speed of light. When matter falls into Sagittarius A, it generates its own subtle gravitational melody, and when the black hole's immense mass moves through space, it leaves a wake of curved space-time that influences everything in its path. These gravitational waves are incredibly weak by the time they reach us, far too subtle to detect with our current technology. The waves generated by Sagittarius A's normal activities would produce distortions in space-time that are smaller than a fraction of a proton's width. Yet they carry with them information about processes occurring in regions of space where no other form of radiation can escape to tell the tale. Imagine, if you will, a cosmic telegraph system where messages are transmitted not through electromagnetic signals, but through the stretching and compressing of space itself. Every significant event near Sagittarius A, every star that spirals inward, every flare in the accretion disk, every minor fluctuation in the black hole's rotation sends out its own gravitational signature into the universe. Future gravitational wave detectors, far more sensitive than anything we have today, may be able to tune into this cosmic telegraph system and decode the messages it carries. We might learn about the internal structure of Sagittarius A by analysing the gravitational waves it produces. We might discover new physics by studying how these waves behave in the intense gravitational fields near the event horizon. We might even catch gravitational echoes from the black hole's formation billions of years ago. But gravitational waves represent just one facet of the information flowing outward from our galactic centre. The electromagnetic radiation produced by the superheated plasma around Sagittarius A carries its own rich catalogue of data about conditions near the event horizon. Each photon that escapes from the accretion disk has been shaped by its journey through the warped spacetime around the black hole, carrying information about magnetic fields, particle densities, and the fundamental physics of matter under extreme conditions. Recent advances in radio astronomy have allowed us to create increasingly detailed maps of the region immediately surrounding Sagittarius A. These maps reveal structure on scales approaching the event horizon itself, a resolution equivalent to reading a newspaper on the Moon from Earth. At these extraordinary magnifications, we can see individual streams of plasma spiraling inward, magnetic field lines twisting and reconnecting, and the complex interplay between gravity and electromagnetism that governs the black hole's behaviour. What emerges from these observations is a picture of Sagittarius A as not just a simple gravitational well, but as a complex engine that processes matter and energy in ways we're only beginning to understand. The accretion disk isn't a uniform, smooth structure, but rather a turbulent, three-dimensional landscape of magnetic flux tubes, shock fronts, and density variations. It's like looking at a cosmic weather system where storms are made of plasma heated to billions of degrees and powered by the fundamental forces of nature. The magnetic fields in this environment are particularly fascinating. Near the event horizon, they become so strong that they dominate over gravity itself in determining how matter behaves. These fields can channel plasma into narrow jets that shoot outward at nearly the speed of light, or they can create magnetic bottles that trap high-energy particles for extended periods. The interplay between magnetic forces and gravitational effects creates a rich ecosystem of phenomena that we're only just beginning to catalogue. One of the most intriguing recent discoveries is evidence for magnetic field lines that may actually thread through the event horizon itself. In classical physics, nothing can escape from inside a black hole. Not matter, not energy, not even information. But magnetic field lines are not material objects. They're geometric features of spacetime. The question of whether they can connect the interior of a black hole to the external universe touches on some of the deepest mysteries in theoretical physics. If magnetic field lines do indeed penetrate the event horizon, they could provide a mechanism for extracting energy from the black hole's rotation, a process known as the Penrose mechanism. This energy extraction could power the jets and outflows we observe from active black holes, explaining how these objects can shine more brightly than entire galaxies, despite being fundamentally dark. The study of these magnetic processes around Sagittarius A is thus providing insights into one of the most exotic energy sources in the universe. The rotation of a black hole represents an enormous reservoir of energy, in the case of Sagittarius A, roughly equivalent to the rest mass energy of our entire Sun. If even a small fraction of this rotational energy can be tapped through magnetic processes, it could power phenomena of incredible violence and beauty. But perhaps the most profound insights coming from our study of Sagittarius A concern the nature of information itself. One of the great paradoxes of black hole physics is the question of what happens to information that falls past the event horizon. According to quantum mechanics, information cannot be destroyed. It can only be scrambled or hidden. But according to general relativity, anything that crosses the event horizon is gone forever, causally disconnected from the external universe. This paradox, known as the information paradox, has puzzled physicists for decades. Some proposed solutions involve the creation of firewalls at the event horizon, regions of intense energy that would destroy anything attempting to cross the boundary. Others suggest that the event horizon is not a true boundary at all, but rather a kind of holographic surface that encodes information about the black hole's interior in patterns too subtle for us to detect. Recent observations of Sagittarius A may be providing the first hints about how this paradox is resolved in nature. The detailed structure of the accretion disk, the precise timing of flares and outbursts, the polarization patterns of emitted radiation. All of these phenomena may carry encoded information about the black hole's interior structure and history. If we could decode this information, we might learn not just about what Sagittarius A is doing now, but about everything it has consumed over its billions of years of existence. The implications of solving the information paradox extend far beyond black hole physics. They touch on fundamental questions about the nature of reality itself. Is information truly fundamental to the universe, more basic even than matter and energy? Do the laws of physics ensure that no information can ever be truly lost, even in the most extreme environments imaginable? These questions connect black hole research to some of the deepest problems in quantum mechanics and cosmology. As we continue to study Sagittarius A with ever-improving technology, we're not just learning about a single black hole in our galaxy. We're exploring the fundamental limits of physical law. We're testing the boundaries between the classical and quantum worlds. We're investigating the relationship between information and reality in the most extreme laboratory nature provides. The monster at the center of our galaxy has become our teacher, showing us aspects of the universe that we could never have imagined from our comfortable perch in the outer regions of the Milky Way. Every observation, every measurement, every subtle detection of polarized light or gravitational influence is like a lesson in a cosmic classroom where the curriculum covers the deepest mysteries of existence itself. Perhaps most remarkably, this education is happening in real time. Unlike distant quasars or ancient supernovae, Sagittarius A is close enough that we can observe its behavior on human timescales. We can watch the hotspot in its accretion disk complete orbits in just over an hour. We can track the orbital motions of nearby stars from year to year. We can observe flares and outbursts as they happen, catching the black hole in the act of processing matter and energy. This temporal proximity gives us something unprecedented in astronomy: the ability to conduct controlled observations of extreme physics. We can predict when certain stars will make their closest approaches to the black hole and prepare our instruments to catch the resulting gravitational light show. We can monitor changes in the accretion disk and correlate them with variations in electromagnetic emission across the entire spectrum. It's rather like having a laboratory experiment that we can observe but not control, where the experimental apparatus is a 4 million solar mass black hole, and the test conditions involve physics at the very limits of what's possible in our universe. The data we're collecting from this natural laboratory is already challenging our theoretical models and forcing us to develop new mathematics to describe what we observe. But perhaps the most beautiful aspect of studying Sagittarius A is how it connects the largest scales of cosmic structure to the smallest scales of fundamental physics. The gravitational influence of our galactic center black hole extends across the entire Milky Way, organizing the motion of hundreds of billions of stars. Yet the most important physics is happening in a region smaller than our solar system, where quantum effects and general relativity merge in ways we're still struggling to understand. This connection between scales reveals something profound about the nature of complexity in the universe. The same physical laws that govern the behavior of subatomic particles also determine the large-scale structure of galaxies. The monster at our galactic center is simultaneously a quantum object, existing in superposition states and governed by probability, and a classical object, massive enough to warp spacetime across thousands of light years. Understanding how these different descriptions of reality fit together, how quantum mechanics and general relativity merge at the event horizon, may be the key to developing the long-sought theory of quantum gravity. Sagittarius A is providing us with observational data that could guide this theoretical development, showing us which mathematical frameworks are consistent with nature and which are merely elegant abstractions. As our observational capabilities continue to improve, we're approaching a remarkable threshold. Within the next decade, we may be able to directly observe the photon sphere around Sagittarius A, the region where light can orbit the black hole in unstable circular paths before either escaping to infinity or falling past the event horizon. We may be able to map the space-time geometry around the black hole with sufficient precision to detect deviations from Einstein's predictions. We may even be able to observe what happens when individual stars make their closest approaches to the event horizon, watching in real time as stellar material is stripped away and processed by the black hole's gravitational mill. These observations would provide our most direct view yet of matter, in the final moments before it crosses the boundary between the known and unknowable. The story of Sagittarius A is still being written. Each new observation adds another chapter to our understanding of how the universe works at its most extreme limits. Each technological advance allows us to peer deeper into the heart of darkness and discover new phenomena that challenge our preconceptions about the nature of space, time, and matter. But in the end, perhaps the most remarkable thing about Sagittarius A is not its extreme physics or its influence on galactic structure, but what it tells us about our place in the cosmic order. We live in a universe where the most violent, destructive objects also serve as the organizing principles for the largest structures, where chaos and order, creation and destruction, darkness and light are not opposing forces but complementary aspects of a single, magnificent reality. The monster at the center of our galaxy is not our enemy. It is our anchor, our organizer, our teacher, and in a very real sense, our creator. The stable galactic environment that allowed our solar system to form, our planet to cool, and life to evolve exists because of the gravitational influence of Sagittarius A. We are children of the black hole, products of its ability to maintain order in the cosmic chaos. As we've journeyed together through the mysteries of our galactic center, we've discovered that reality is far stranger, far more beautiful, and far more interconnected than our everyday experience suggests. The invisible giant that anchors our galaxy operates according to physical laws that bend our understanding of space and time. It creates conditions that challenge the boundaries between the possible and impossible, the known and unknowable. And yet, for all its exotic physics and extreme conditions, Sagittarius A is part of the same universe that gave rise to stars and planets, to chemistry and biology, to consciousness and wonder. The same quantum fields that dance around its event horizon also give rise to the atoms in your body. The same space-time that curves around its massive presence also carries the gravitational waves that keep Earth in orbit around our Sun. In studying the monster at the center of our galaxy, we are ultimately studying ourselves, understanding the cosmic processes that made our existence possible and the physical laws that govern our place in the universe. We are mapping the territory of the extreme to better understand the familiar, exploring the darkness to better appreciate the light. The journey into the heart of our galaxy is also a journey into the heart of physics itself, where the most fundamental questions about the nature of reality await answers. And perhaps that is the most profound lesson Sagittarius A has to teach us, that the universe is not divided into separate realms of the ordinary and the extraordinary, but is a single, unified whole, where every scale from the quantum to the cosmic is connected in an intricate web of cause and effect. As you settle into sleep tonight, remember that you're part of this cosmic web, connected to every star in our galaxy through the invisible threads of gravity that emanate from the monster at its center. You are riding on a planet that orbits a star, that orbits a black hole, participating in a dance that has been going on for billions of years and will continue for billions more. Sweet dreams, fellow travelers. May your rest be peaceful, and may your dreams be filled with the wonder of our magnificent, mysterious universe. But our exploration of cosmic extremes doesn't end here. If the warping of space-time around Sagittarius A has captured your imagination, you might find yourself wondering about an even more fundamental question. Is the very fabric of reality, the space-time that black holes bend and twist, actually real? Or is it merely an illusion created by deeper, more fundamental processes? That's a mystery that takes us beyond even black holes, into the realm where physics meets philosophy and where the nature of existence itself comes into question. Next time, we'll embark on a journey into the deepest foundations of reality itself, exploring the possibility that space-time, the very stage on which all cosmic dramas play out, might be nothing more than an emergent property of something far more strange and wonderful than we've ever imagined. Until then, rest well, and thank you for joining me on this journey to the heart of darkness and back to the light. There's a peculiar comfort in cycles, isn't there? The sun rises and sets, seasons change and return, tides ebb and flow with mathematical precision. But what if I told you that the monster at the center of our galaxy follows its own vast cosmic rhythm, one that spans not days or years, but millions of centuries? What if the seemingly random flares and quiet periods of Sagittarius A are actually part of a grand clockwork mechanism that's been ticking away since before Earth existed? The discovery of this cosmic heartbeat began with a puzzle. When astronomers first started monitoring the galactic center across different wavelengths of light, they expected to find either steady activity or completely random variations. Instead, they uncovered something far more intriguing: patterns within patterns, cycles within cycles, a complex temporal symphony that suggests Sagittarius A operates according to rhythms we're only beginning to understand. Consider the Fermi bubbles we discussed earlier, those enormous structures of superheated gas extending above and below our galactic plane. Recent analysis suggests these bubbles weren't created by a single catastrophic event, but rather by a series of periodic outbursts separated by roughly 10 million years. It's as if our galactic center operates like a cosmic geyser, building up pressure over geological timescales before releasing it in spectacular displays of energy. But these million-year cycles are just the largest notes in a much more complex composition. Embedded within them are shorter rhythms, cycles of stellar formation and destruction that repeat every few 100,000 years, variations in the accretion rate that oscillate over millennia, and the rapid-fire flickers we observe on timescales of hours and days. This nested hierarchy of temporal patterns reveals something profound about the nature of complex systems in the universe. Just as your heartbeat maintains its rhythm while being influenced by breathing, exercise, and emotion, Sagittarius A maintains its cosmic pulse while responding to the ever-changing gravitational dance of stars, gas clouds, and dark matter in its vicinity. The implications of this cyclical behavior extend far beyond our galactic center. If supermassive black holes operate according to predictable patterns, it suggests that galactic evolution itself might be more deterministic than we previously imagined. The seemingly chaotic process of galaxy formation and evolution might actually follow hidden rules, cosmic algorithms that play out over billions of years. Think of it this way. Imagine watching a city from space over the course of a single day. You'd see seemingly random patterns of light appearing and disappearing, traffic flowing in apparently chaotic directions, activity that looks completely unpredictable. But zoom out in time, observe for weeks or months, and patterns emerge: rush hour cycles, seasonal variations, the rhythms of human activity that repeat with clockwork regularity. Our observations of Sagittarius A may be revealing similar patterns in the life of our galaxy. What appears chaotic on human timescales might be part of orderly cycles when viewed from the perspective of cosmic time. The monster at our galactic center might be less of a wild beast and more of a cosmic metronome, keeping time for processes that span the history of the universe. Recent computer simulations have begun to explore what drives these cycles. The models suggest that the periodic outbursts from Sagittarius A's might be triggered by the orbital mechanics of massive gas clouds in the galactic center. As these clouds follow their elongated orbits around the black hole, they periodically pass through regions where they can be efficiently accreted, leading to episodes of enhanced activity separated by long periods of relative quiet. It's rather like a cosmic version of Halley's Comet, except instead of a ball of ice and dust making a periodic approach to the Sun, we have gas clouds with the mass of millions of suns making periodic approaches to a black hole. Each passage triggers a feeding frenzy that can last for thousands of years, followed by a long fast as the black hole waits for the next course to arrive. But the story becomes even more fascinating when we consider the role of stellar dynamics in this cosmic clockwork. The population of stars orbiting near Sagittarius A is constantly changing. As new stars are born, old stars die, and occasional visitors from the outer galaxy make brief appearances in the central region. Each of these stellar events influences the feeding patterns of the black hole, creating a complex feedback loop between stellar evolution and black hole activity. Some of the most intriguing possibilities emerge when we consider what happens during the peak phases of this cycle. When Sagittarius A enters one of its active periods, the increased radiation and particle outflows can dramatically affect star formation throughout the inner galaxy. Regions that were previously forming stars at a steady rate might suddenly find their gas clouds heated and dispersed by the black hole's energetic output. Conversely, the shock waves generated by these outbursts might compress gas in other regions, triggering bursts of star formation that wouldn't have occurred otherwise. The result is a kind of cosmic breathing pattern, where the activity of the central black hole alternately suppresses and enhances star formation across vast regions of our galaxy. This breathing pattern has profound implications for the development of planetary systems like our own. Our solar system formed roughly 4.6 billion years ago, during what appears to have been a relatively quiet phase in Sagittarius A's activity cycle. Had we formed during one of the black hole's active periods, the increased radiation and stellar winds might have stripped away the atmospheres of the inner planets, preventing the development of conditions suitable for life. It's a sobering reminder of how interconnected cosmic processes really are. The timing of our solar system's formation, the stability of Earth's climate over geological time, even the rate at which complex life has evolved. All of these might be influenced by the cyclical behaviour of a monster located 26,000 light-years away. But perhaps the most remarkable aspect of these cosmic cycles is how they connect the smaller scales of physics to the larger scales of cosmic structure. The quantum mechanical processes occurring near Sagittarius A's event horizon influence the behaviour of the accretion disk, which affects the black hole's feeding rate, which determines the energy output, which shapes the galactic environment, which influences star formation, which affects the chemical evolution of the galaxy. It's an unbroken chain of cause and effect that links the behaviour of individual particles to the fate of entire stellar populations. The monster at our galactic centre doesn't just warp space-time, it weaves together all the scales of cosmic organisation into a single, coherent pattern. Recent observations have begun to reveal how these patterns manifest in the present day. The James Webb Space Telescope's detailed monitoring of Sagittarius A has shown that even the rapid flares we observe on timescales of hours and minutes follow subtle patterns. Certain types of flares are more likely to occur at specific orbital phases of nearby stars. Others correlate with the passage of gas clouds through particular regions of the accretion disk. These correlations suggest that the black hole's environment is far more structured and predictable than the chaotic maelstrom we might expect. Instead of random violence, we see organized complexity, a cosmic ecosystem where every component influences every other component in predictable ways. Understanding these patterns has practical implications for our ability to predict future behavior. If we can decode the rules governing Sagittarius A's cyclical activity, we might be able to forecast when the next major outburst will occur, how it will affect the galactic environment, and what consequences it might have for star formation and planetary evolution throughout the Milky Way. Such predictions would represent a new frontier in astrophysics, the ability to forecast cosmic weather on galactic scales. Just as meteorologists use computer models to predict earthly weather patterns, future astronomers might use galactic models to predict the activity cycles of supermassive black holes and their effects on their host galaxies. But these cosmic patterns raise deeper questions about the nature of time itself in the universe. If galactic evolution follows predictable cycles, what does that tell us about the arrow of time on cosmic scales? Are we living in a universe that's gradually winding down toward a state of maximum entropy, or one that's cycling through endless repetitions of cosmic seasons? The behaviour of Sagittarius A might provide clues to this fundamental question. If its activity cycles are gradually damping out as the galaxy ages and runs out of fuel for star formation, it would support the traditional view of cosmic evolution as a one-way journey toward increasing entropy. But if the cycles are self-sustaining, powered by the black hole's own gravitational influence on its environment, it might suggest a more cyclical view of cosmic time. Recent theoretical work has explored the possibility that the universe itself might be cyclical, with periods of expansion and contraction, birth and death, playing out over unimaginably vast timescales. In such a cyclical cosmos, the patterns we observe in Sagittarius A might be local reflections of much grander cycles that govern the fate of the universe as a whole. These ideas push us to the very edges of what science can currently address. They connect the detailed observations we make of our galactic centre to the deepest questions in cosmology and fundamental physics. The monster at the centre of our galaxy becomes not just an object of study, but a window into the nature of time, causality, and existence itself. As we continue to monitor Sagittarius A with ever-improving instruments, we're essentially conducting a long-term experiment in cosmic chronometry. Each observation adds another data point to our understanding of how time unfolds in the most extreme gravitational environments. Each measurement helps us decode the temporal patterns that govern galactic evolution. But perhaps the most profound realization emerging from this work is that we are witnesses to these cosmic cycles, participants in their unfolding. The atoms in your body were forged in stars that formed during previous cycles of galactic evolution. The stable environment that allowed complex chemistry and biology to develop exists because of the regulatory influence of Sagittarius A's cyclical behaviour. You are not separate from these cosmic patterns, you are part of them. Your existence is woven into the same temporal tapestry that connects quantum fluctuations near the event horizon to the large-scale structure of our galaxy. The rhythms of your own biological cycles, heartbeat, breathing, sleep, are embedded within the vast cycles of cosmic evolution that have been playing out since the universe began. In the quantum realm surrounding Sagittarius A, something extraordinary is happening that challenges our most basic assumptions about the nature of reality. Recent theoretical developments suggest that the event horizon of our galactic centre black hole might not be the impermeable boundary we once imagined, but rather something far more subtle and strange, a kind of cosmic mirror that reflects information back to the universe in ways we're only beginning to understand. This possibility emerges from one of the most elegant solutions to the black hole information paradox that has been proposed in decades. The idea is deceptively simple, yet profoundly revolutionary. What if the event horizon doesn't actually destroy information, but instead encodes it in holographic patterns that can be read by sufficiently sensitive observers? What if every particle that has ever fallen into Sagittarius A has left a permanent record of its existence imprinted on the black hole's boundary? To understand this concept, imagine watching a movie projected onto a screen. The screen itself is two-dimensional, but the images it displays can represent complex three-dimensional scenes. Similarly, the two-dimensional surface of a black hole's event horizon might encode information about the three-dimensional volume it contains. Every quantum state, every particle interaction, every bit of information that has ever crossed the boundary might be preserved as a pattern in the holographic structure of the event horizon. This holographic principle suggests that Sagittarius A is not just a gravitational monster, but also a cosmic library, a repository of information about every star, every gas cloud, every particle of dark matter that has fallen into it over the past billions of years. The challenge is learning how to read this library, deciphering the holographic code that encodes 4 billion years of galactic history on the surface of our central black hole. Recent advances in quantum information theory have begun to provide the theoretical tools needed for this decoding process. By analysing the subtle correlations between particles in the radiation emitted by black holes, it might be possible to reconstruct information about the black hole's interior. The seemingly random thermal radiation that Sagittarius A emits might actually contain hidden patterns that preserve the quantum states of everything that has ever fallen into it. This process would be extraordinarily subtle and complex, requiring measurements of quantum correlations across vast amounts of Hawking radiation, collected over enormous periods of time. It would be like trying to reconstruct a shredded document by analysing the statistical properties of the paper scraps. Theoretically possible, but practically challenging beyond anything we've ever attempted. Yet the implications of success would be staggering. We might be able to recover information about the early history of our galaxy encoded in the quantum structure of Sagittarius A. We might learn about stellar populations that lived and died billions of years ago, about the formation and evolution of the galactic center, about cosmic events that occurred long before our solar system existed. The holographic principle also suggests a profound connection between the physics of black holes and the fundamental nature of spacetime itself. If information can be encoded on two-dimensional surfaces and yet represent three-dimensional realities, it raises the possibility that all of spacetime might be emergent from more fundamental information processing systems. This idea leads to some of the most speculative but fascinating frontiers in modern physics. Some theorists have proposed that the entire universe might be holographic in nature, that all of three-dimensional reality, including the matter and energy we observe around us, might be projections from information encoded on a two-dimensional boundary at the edge of the observable universe. In this view, Sagittarius A would be more than just a black hole. It would be a local manifestation of a universal principle that connects information, geometry, and reality in ways we're only beginning to glimpse. The patterns we observe in its accretion disk, the correlations we measure in its radiation, the quantum fluctuations near its event horizon, all of these might be windows into the fundamental information processing substrate that gives rise to the appearance of physical reality. These ideas push us far beyond the comfortable realm of observational astronomy into territory where physics and philosophy begin to merge. They force us to confront deep questions about the relationship between information and existence, between computation and reality, between the map and the territory of cosmic structure. But even as we explore these speculative frontiers, the practical study of Sagittarius A continues to yield concrete insights into the nature of extreme physics. Recent observations have revealed new details about how matter behaves in the final moments before crossing the event horizon, providing our most direct view yet of the boundary between the classical and quantum worlds. One of the most intriguing discoveries is evidence for what theorists call quantum hair around the black hole, subtle quantum effects that create tiny deviations from the smooth spacetime geometry predicted by classical general relativity. These deviations are incredibly small, detectable only through the most precise measurements of light bending and particle trajectories near the event horizon. The existence of quantum hair suggests that black holes are not the perfectly smooth, featureless objects described by Einstein's equations, but rather complex quantum systems with rich internal structure. This structure might encode information about the black hole's formation history, its interactions with surrounding matter, and the quantum mechanical processes that govern its evolution. Understanding this quantum structure is crucial for resolving fundamental puzzles about black hole physics. It might explain how information is preserved during black hole formation and evaporation, how the interior and exterior of black holes remain connected despite the apparent barrier of the event horizon, and how quantum mechanics and general relativity can be reconciled in the most extreme gravitational environments. The study of quantum hair around Sagittarius A is also providing new insights into the nature of vacuum itself in curved spacetime. The event horizon, the intense gravitational fields, can actually create particles from empty space through a process called vacuum polarization. Virtual particle pairs that would normally annihilate each other can be separated by the black hole's tidal forces, with one particle falling inward while the other escapes to become real radiation. This process, known as Hawking radiation, was predicted theoretically decades ago, but has never been directly observed due to its incredible weakness. For a black hole the mass of Sagittarius A, the temperature of Hawking radiation is less than a billionth of a degree above absolute zero, far too cold to detect with any current technology. Yet indirect evidence for Hawking radiation might be hidden in the subtle statistical properties of the electromagnetic radiation we do observe from the galactic center. Recent theoretical work suggests that quantum correlations between Hawking radiation and the thermal emission from the accretion disk might create detectable signatures in the polarization and timing of observed photons. Detecting these signatures would represent one of the greatest triumphs in the history of physics, direct confirmation of one of the most remarkable predictions of quantum field theory in curved spacetime. It would also open new experimental windows into the quantum nature of gravity, providing empirical data to guide the development of theories of quantum gravity. But perhaps the most profound implication of the holographic principle and quantum hair is what they suggest about the nature of emergence in physical systems. Just as the complex behavior of living organisms emerges from the interactions of simple molecules, the classical physics we observe on large scales might emerge from quantum information processing on microscopic scales. Sagittarius A serves as a natural laboratory for studying this emergence, a place where quantum effects scale up to produce observable consequences on astronomical scales. The patterns we see in its accretion disk, the correlations we measure in its radiation, the gravitational effects we detect through stellar orbits, all of these might be emergent properties of quantum information processing occurring near the event horizon. This perspective transforms our understanding of what black holes actually are. Instead of being exotic, but ultimately simple objects defined by their mass, charge, and angular momentum, they become complex information processing systems that encode and manipulate quantum data in ways we're only beginning to understand. The implications extend far beyond black hole physics to touch on some of the deepest questions in science and philosophy. If physical reality emerges from information processing, what does that tell us about the nature of consciousness, which also appears to be fundamentally concerned with information integration and processing? Are there connections between the quantum information processing occurring near Sagittarius A and the neural information processing occurring in biological brains? These questions remain highly speculative, but they illustrate how the study of our galactic center black hole connects to the broadest possible range of human inquiry. The monster at the center of our galaxy is not just an astronomical object, it's a cosmic laboratory where the fundamental principles that govern reality itself are displayed in their most extreme and pure form. As we continue to probe deeper into the quantum structure of Sagittarius A, we're engaged in something far more profound than astronomy. We're exploring the foundations of existence itself, investigating the relationship between information and reality, between the quantum and classical worlds, between the computational and the physical aspects of the universe. Each new observation, each theoretical advance, each subtle correlation detected in the data brings us closer to understanding not just how black holes work, but how reality itself is constructed from the interplay of information, geometry, and quantum mechanics. The journey into the heart of darkness has become a journey into the heart of existence, where the deepest questions about the nature of being await their answers. And as we stand at the threshold of these discoveries, poised to unlock secrets that have remained hidden since the universe began, we can't help but marvel at the extraordinary journey that has brought us here. From the first detection of radio waves from the galactic center to the recent images of the event horizon, from the discovery of stellar orbits to the detection of gravitational waves, the story of Sagittarius A has been a story of human curiosity and ingenuity pushing the boundaries of what's possible. But the story is far from over. The monster at the center of our galaxy still holds secrets that may revolutionize our understanding of space, time, information, and reality itself. As we continue this exploration, we're not just studying a black hole, we're studying the universe's deepest principles, the fundamental codes that govern how existence unfolds from moment to moment across all scales of space and time. In the end, perhaps that's the most remarkable thing about Sagittarius A, not its immense mass or its ability to warp space-time, but its role as a teacher, showing us aspects of reality that we could never have discovered any other way. The monster at our galactic center has become humanity's greatest professor, offering lessons in physics that transform our understanding of what it means to exist in this strange, beautiful, quantum universe we call home. Sweet dreams, fellow explorers, and remember, even as you sleep, you're traveling through space at incredible speeds, held in the gentle gravitational embrace of the cosmic teacher that anchors our galaxy, guides our evolution, and reveals to us the deeper secrets of existence itself. If the holographic mysteries of black holes have stirred your curiosity about the fundamental nature of reality, you might find yourself wondering about an even more basic question that connects to everything we've explored tonight. What if the very stage on which all these cosmic dramas unfold, what if space-time itself, the fabric that black holes bend and warp, isn't actually real at all, but merely an illusion emerging from deeper, more fundamental processes? That's a question that takes us beyond black holes, beyond astronomy, into the very foundations of what we call reality. Until then, rest well, and thank you for joining me on this journey through the heart of darkness and into the light of understanding. But there's something even more extraordinary happening right now, as you settle into these final moments of our cosmic journey. Every atom in your body, every breath you take, every neural firing in your brain exists within what might be the most sophisticated information storage system ever discovered. The holographic surface of Sagittarius A's event horizon isn't just preserving the history of our galaxy, it's weaving your story into the fabric of space-time itself. Think about this for a moment. The light reflecting off your skin right now will eventually make its way across the galaxy. Some of those photons will interact with the accretion disk around our central black hole, carrying information about this exact moment. Your thoughts, your breathing, even the quantum states of the atoms in your retinas, into the holographic record that surrounds Sagittarius A. Hey. In a very real sense, you're already part of the monster's memory. This realization brings us to perhaps the most beautiful paradox in all of physics, the object that represents ultimate destruction, a gravitational well so deep that nothing can escape, has revealed itself to be the universe's most perfect archivist. Every star that has lived and died, every planet that has formed and been consumed, every thought that has ever been thought near the galactic center becomes part of an eternal library written in the quantum geometry of curved space-time. Recent calculations suggest that the information storage capacity of Sagittarius A's event horizon exceeds anything we can comprehend. If we could somehow decode the holographic patterns encoded on its surface, we might recover not just the physical history of our galaxy, but the complete quantum states of every system that has ever interacted with the black hole's gravitational field. It would be like having access to a cosmic hard drive that has been recording the universe's data for over 13 billion years. And so we find ourselves at the end of our journey into the heart of darkness, though perhaps end isn't quite the right word, because in studying Sagittarius A, we've discovered that endings and beginnings are far more intertwined than we ever imagined. The monster at the center of our galaxy doesn't just consume, it preserves, it organizes, it teaches, and in ways we're only beginning to understand, it creates. Tonight we've traveled from the first whispers of radio waves detected nearly a century ago to the quantum mysteries that challenge our deepest understanding of reality itself. We've seen how this invisible giant shapes not just the architecture of our galaxy, but the very conditions that make consciousness possible. We've discovered that you are not separate from this cosmic dance. You are part of it, woven into the same gravitational symphony that has been playing for billions of years. The story of Sagittarius A is ultimately the story of connection. It connects the smallest scales of quantum mechanics to the largest scales of cosmic structure. It connects the past to the future through its holographic memory. And it connects us, fragile, curious beings on a small planet, to the fundamental forces that govern the universe. As you drift towards sleep tonight, carry with you this thought. The same space-time that curves around our galactic center also flows gently around you. The same quantum fields that dance at the event horizon also give rise to the neurons firing in your brain. You are made of star stuff held together by forces born in the heart of darkness, participating in a cosmic story that's still being written. If you've enjoyed this gentle exploration into the deepest mysteries of our galaxy, I'd be grateful if you considered subscribing to the Sleepy Physicist. And if tonight's journey through the nature of black holes and reality has stirred your curiosity about the very foundation of existence itself, you might find yourself wondering about our next exploration. Space-time fabric. Is reality just an illusion? Until then, sleep well, dream deeply, and remember, in this vast, strange, beautiful universe, you are exactly where you belong. You are exactly where you belong.